AI at Stanford was pioneered by John McCarthy. This conference comes roughly 50 years after his Turing Award lecture on the present state of research in artificial intelligence. In it, McCarthy focused on the issue of generality in artificial intelligence systems. Last fall, HAI launched the Center for Research on Foundation Models, led by Stanford professor Percy Liang, who you'll be hearing in our next group of speakers. CRFM is an interdisciplinary team of more than 100 researchers that aims to make fundamental advances in the development, deployment, analysis, and safeguarding of large pre-trained models for language and their generalization to other data modalities, such as in the just-released DALL-E 2 model from OpenAI, which we're also likely to hear about later in this session. We think that this is a very exciting time in the development of AI with these new foundation models, which are the first big breakthrough in addressing the lack of generality of earlier AI models. Indeed, these models have generated an enormous amount of excitement in the past year, so we hope that this will be a very lively discussion. Please join me in welcoming Percy Liang, Sarah Bana, Cordelia Schmid, Ilya Sutskever, and Reich. Our first speaker today is Associate Professor Percy Liang of Stanford, Director of our Center for Research on Foundation Models.
All right, thank you, Chris, for that wonderful introduction and setting the stage here. So I'm really excited to be here in person, and hello to everyone online as well. Last week was quite a week. Many of you probably have heard the news of Google releasing their large language model, PaLM, which outclasses GPT-3 and can do all sorts of different capabilities, such as explaining jokes, among other things. And not to be outdone, OpenAI released DALL-E 2 2 days later, which I'm sure Ilya will talk about, which can take captions and generate photorealistic images such as that teddy bear, which you've seen on a previous talk already. These two models are examples of a larger class of what we call foundation models. Foundation models are models which are trained on broad data, usually at immense scale in a self-supervised way, and that can be quickly adapted to a wide range of downstream tasks. And there are many examples of foundation models, some of which are listed here, some of which you've heard about. And one thing that I think is really significant about foundation models is that it changes the paradigm in which AI systems are built. So rather than having bespoke models for each individual task, now you train a general purpose foundation model that can be adapted across a wide variety of different scenarios. So I should underscore, though, that foundation models are raw and unfinished. And they're, by their very nature, they're a foundation, not the complete house. And there's work that needs to be done to turn them into actual applications. So there are things that you might not necessarily want to release to 1 billion users. And how to do this adaptation responsibly is an active area of discussion, which we'll hopefully discuss more about. So we recognize the importance of foundation models. And last year, we started a Center for Research on Foundation Models, as Chris talked about. Now it's over 200 students, postdocs, and faculty. And one thing that's really remarkable is how interdisciplinary the team is. So last year, we put out a massive report explaining the opportunities and risks of foundation models. We released some open source software to help people train foundation models, and we also held a workshop on inviting the entire community to engage on this topic. This year, and in the remaining of the talk, I want to highlight a few examples of the work that's happening at the center right now, which are roughly grouped into 3 categories. So the first is social responsibility, in which we are trying to benchmark and document the existing models out there, develop community standards, and also think about how these models are actually impacting people's lives. We are also making progress on technical advances, developing new model architectures, principled ways of defining new objective functions, and so on. And finally, we're looking at different applications, both general purpose capabilities such as privacy and robustness to distribution shift, but also ways in which the writers and designers can use these models in different ways, as well as whole areas such as law and medicine, which are kind of under kind of explored. So in the remainder of the talk, I want to highlight spotlight 7 of these projects in maybe 3 minutes or so. So we'll see how far we can get. So the first I wanted to talk about, this is a collaboration with Erik Brynjolfsson, where we're trying to understand we know foundation models are capable, but what is their impact on the economy? We look at kind of the total wage bill of writing occupations, as well as kind of individual impact on writers who are trying to use tools such as GPT-3 to do tasks such as copywriting. On the improvement of model side, transformers are the workhorse of modern foundation models. But they have one big deficiency, is that they're not very good at modeling very extremely long-range dependencies, which, you think about audio or video, presents problems. So this is work by Chris Ray's group, where they went back to the 1970s control theory literature, and where they had explored models of thinking about long sequences, and designed something called structured state space sequence models, S4. And they show that these models are much more accurate and efficient than transformers on a task such as speech classification. And furthermore, they actually are more robust to differences in sampling rates. So this is very exciting. We also looked at the question of what are the right training objectives, because there are so many ways you can train a foundation model. How do you navigate the space? And we asked a very naive question: what is an optimal foundation model or representation? Now, with some assumptions, we came up with the idea that the representations are ways ones that can predict the equivalence class. Now, this is impossible to actually implement, but if you approximate it, this leads to a number of insights that allow us to improve over the state of art on some image benchmarks. Now, looking at ways that we can use foundation models. So domain adaptation is a critical problem, because ML systems are known to be unreliable when you train them on a source domain and you try to adapt them to a target domain. But we show that if you train a foundation model on the union of the unlabeled data from source and target, and you simply fine-tune on the source, that actually beats classic unsupervised domain adaptation methods, suggesting kind of the generality of foundation models, which wasn't specifically designed for this purpose. Privacy came up in the previous session, where we want to try private models. But the problem is that when you ensure differential privacy, you had to add noise, and that hurts your accuracy. So one promising way to get around that is to train a foundation model on public data, such as Wikipedia, and then you can fine-tune on your private data. And we show that if you have the right setup, you can actually train these large differentially private language models based on public foundation models that are both accurate and private. So another collaboration is with Michael Bernstein from HCI, and here the context is you want to design a social computing platform. You want to create a subreddit, but you're curious, how will people interact with it? Is it going to be dominated by internet trolls and so on? And we found that GPT-3 was actually a really good tool for enabling designers to generate human personas, goals, and interactions, which are all simulated, but give the designer an idea of what's plausible. And this is interesting because foundation models are trained on internet data, and usually this is a bad thing because it inherits all the kind of ugliness of the internet. But in this case, it's actually right because you want to simulate what would happen on the actual internet. A final example comes from a colleague, Akshay Chaudhary from radiology. And here, there's a massive opportunity here where even at Stanford, we're sitting on petabytes of medical imaging data. And the goal here is to train a foundation model that can power a wide variety of downstream medical imaging tasks. And here, the medical images are interesting because they're very different from internet images. So you see that green rectangle. there's a white blip. Is that noise, or is it actual indication of a serious kind of medical illness? And so some of the classical techniques don't really work in this setting. So there are many other projects I could mention, but hopefully this gives you a taste of what's been happening at CRFM. Maybe I could distill it down into kind of 3 themes. One is that foundation models are super impressive. They've been used in a lot of different settings, but they're far from optimal in terms of efficiency, robustness, bias, and all these things. And I think one of the things we're doing at CRFM is to go back to first principles and think, how do we design these models so that they can be much better than they are right now? The second point is that foundation models, you think most people probably have in their mind this teddy bear in Times Square, right? But I want to emphasize that foundation models are really useful for these kind of general capabilities, such as robustness and privacy, which are part of kind of the responsible AI session that we heard about. And foundation models in these cases actually gives you a substantial lift. And finally, while a lot of foundation models you hear about are focused on kind of internet applications, I want to emphasize that there's actually many more opportunities across a vast variety of disciplines, represented at Stanford across law and medicine and other sciences, and where there's a lot of data that you can harness the power that we've learned about through foundation models and make other discoveries in these fields. So with that, I'll end there, and thanks for your attention.
Thank you very much, Percy. Our next speaker is Sarah Bana, a postdoctoral fellow at the Stanford Digital Economy Lab.
Thanks so much, Chris, for the introduction, and thanks so much, Percy, for leading or ending with the applications. I think that what this project is it's really an application of foundation models to social science research, and I'll talk a little bit about my work as well as other opportunities for social science research. So where I'm coming from is thinking about a foundation model to provide new insights into the age-old question of what determines wages. Economists have spent decades trying to decompose wages into a variety of different elements. But one major problem is data constraints. So survey data, for example, one place where you can ask people their wages and what they do, is constrained because the more questions you ask, the more costly it becomes. The more people you ask, the more costly it becomes. Administrative data might be one potential solution to this problem, but in the United States at least, occupation or what people do is not collected in administrative data. However, online job search provides a tremendous opportunity. Us being searching for jobs online and employers posting for jobs online gives us a digital trace in terms of what employers want as rich text in the form of online job postings. So what I do is I start to use a foundation model to answer the question of salary determination. Fundamentally, I'm interested in whether or not words matter for salary determination and whether or not we can predict salaries from the text of job postings. How well can we predict these, and if so, how do they compare to other benchmarks? If they are indeed valuable, what can the text of job posting tell us about what employers value in terms of attributes like different skills, titles, locations, and other attributes of jobs? To answer this question, we assemble a large data set with over 1 million job postings from 2019 by combining multiple different vendors' data. The critical attribute in this data is recruiter inputted salary bands. The job postings data has postings from a variety of different domains, like this clinical research coordinator 2 at Stanford University's Department of Pediatrics. So that's a pretty near job posting, but plenty of far ones as well, like this aircraft maintenance technician for UPS in Anchorage, Alaska, and also spans a variety of different domains, including this entry-level server at my sister's favorite hot pot restaurant near my hometown. because these postings have such a wide variety of domains, a variety of different words are also used in those postings, and that's where large language models come in. So what I do is I fine-tune a BERT model for the task of salary prediction, estimate on out-of-sample postings, and then compare to a variety of different baselines. In this talk, I'll focus on the measure of how much variation the model is able to explain. That's sometimes called coefficient of variation, or R squared. I can show you a measure like root mean squared error, but I find coefficient of variation to be helpful because it's very interpretable, goes between 0 and 100. So it turns out that the BERT-based model does really well. It can explain 83% of the variation in salaries, and that's along the lines of a lot of other applications of BERT to economics. I'm now going to show you a variety of different relevant benchmarks, and I want you to think about these as, I'll talk about how these relate to varieties of different data we currently have. So first, occupation fixed effects. Occupation fixed effects means that we allow for a different occupation intercept for around the 800 occupations that exist in the data, and that explains just under 60% of the variation. We also know that location matters, and so we can add different intercepts for different occupations by locations, and we find that that explains just under 70% of the variation in the data. I want you to think about that benchmark, occupation by location, as the level of data that government surveys like the Current Population Survey currently collect. Now I'll do two sort of thought experiments, one with very broad skill groups like IT skills or legal skills or design skills, and then the other one with more specific skills like cybersecurity or artificial intelligence. And what you can see is that these two models still underperform compared to the BERT-based model. But you can imagine being asked, let's say, 28 or 648 different questions on a survey, or alternatively, your employer being asked whether or not your job requires all these different skills on a survey. And that's a huge burden. And even then, it still underperforms the BERT-based model, which has activities, skills, locations, but also things like experience levels, technologies used, and a variety of other information. So now, hopefully, I've convinced you at least a little bit that job postings have a tremendous amount of information, and we can leverage that information. A natural next question is, which tokens or words play an outsized role? To get at this, I'm going to use an attribution method called integrated gradients. I just want you to think about perturbing a given word or a given token and how that's going to affect the salary attribution process. And so these are just a couple select examples. So I've listed a bunch of activity-related words, and you can see the word manage is associated with a positive effect, or educate also being associated with a positive effect, but the word clean or assemble potentially being associated with a negative effect. These words also have mathematical interpretations. That is, for example, the inclusion of the word evaluate is associated with a 0.0002% increase in salary. Now, that might be small, but it's actually statistically significant. And I want you also to think about this as the effect of a single word in a job posting on salary. We can also look at technologies and see mostly positive attributions for technology skills. The Microsoft Office suite, not so much, but skills like SQL, Java, Python, a lot of the skills that we use in our work are associated with positive effects. So I see a tremendous number of applications of foundation models to social science research. I'll just briefly talk about one. I'm sure you've heard a lot of discussion about inflation nowadays. Inflation is actually really challenging to calculate because of the fact that products come and go. But Pat Bahari and co-authors have used product descriptions on Amazon combined with BERT to develop a hedonic pricing model and values of given features of goods. And what they can do is develop even better algorithmically defined price indices. So the big finding from their paper is that consumer welfare actually went up between 2013 and 2017 as a result of quality increases. So there's plenty more papers. I just wanted to point out that most of these are all came out or have been revised in the past couple years. And so there are plenty of opportunities in social science, and hopefully we'll be able to talk about a few more of them. So thanks so much, everyone, for your time.
Thank you very much, Sarah. Next, I would like to welcome Cordelia Schmid, a research director at Inria and a research scientist at Google, who's joining us virtually. I hope you can hear us okay, Cordelia?
Yeah, hello?
Hello? Yes, we can hear you. Okay, if you could please go ahead with your talk.
All right, let me share my screen. Right. Okay, can you see my screen? Hello?
Yes, we can see your screen and slides.
Can you hear me?
Yes.
Okay, perfect. So yeah, thank you for the introduction. And so I'll give 2 examples for large-scale multimodal learning. And so basically, what are the open questions? One of the open questions is actually when training these large-scale models, which training data to use. So this has been a recurring issue in computer vision for a long time. But if we have these large models and large-scale data which is available, it's even more important to actually know which data we use to train these models. Only if we know which data we use can we really understand what is contained in them. And another thing which is important, that we have this multimodal information which is available. Video data, which comes with speech, audio. Speech can be transcribed by ASR into text, can have textual metadata. So we have this concurrent information which is available and which can be very well captured by these foundation models. One thing is, you have also heard before, is that many downstream tasks are possible, and they're completely new tasks which are now possible, such as vision, language, and navigation, robotics, multimodal translation, multimodal ASR, and many more. And then one thing which was also mentioned, which is becoming increasingly more important, is to develop alternative models which have possibly less parameters and can span larger time ranges. So for now, the time spans are still limited. I'll now show 2 of our recent examples. The first one for data curation, which uses cross-modal supervision, and the second one for a new task, which is a transformer-based model for vision, language, navigation. So what's the idea of our cross-modal supervision? Just ask. So the task we want to solve is, given a short video clip and a question. So here, for example, what type of animal do we see? We want the system to give the answer. Here, the correct answer, which is produced by our system, is our fish. And so here the idea is that we want to go away from any type of annotated training data, but we want to perform zero-shot vision question answering, and to obtain the examples, use the cross-modal supervision. I'll explain in a while how this works. And this allows question answering dataset automatically. 96 million question answer pairs plus corresponding video clips. The idea is the following. We take a large scale dataset, here how to 1M, which comes with video clips and the speech transcribed with ASR. So for each clip, we have the corresponding speech transcribed. And given that those are instructional videos, we have, in many cases, a description of what's happening in the video. So for example, here, cut the white felt in circles. Then we have to our disposition a manually annotated text question answering training corpus. So there are text paragraphs corresponding questions and answers. And we can then train a transformer on this data set. And we can then apply this text data transformer to our description of the videos and obtain for a given clip the corresponding question answer. And so we can see here, we have this an example for a generated question answer. We have the video clip, the ASR, the sound is amazing on this piano, and we can then automatically generate the question, what kind of instrument is this sound of? And the generated answer is piano. We then train a transformer on the data. Here we have a transformer which takes as input the video and the question, and another one which takes as input the answer. We can use contrastive loss with positive and negative answers to train our model on this large-scale data set. Here, 16 million different answers. And then we can evaluate this for zero-shot vision question answering. So we don't use any annotated training examples, but we evaluate the results on standard test data of standard benchmarks. And we can see the first row shows performance if we give random responses. And the second row shows our results with our zero-shot pre-trained model. And we can see that the performance at top 10, for example, 43% is very good already. Here an example of one of the zero-shot results. The question is, what is the largest object at the right of the man? And the answer is wheelbarrow. And if you would use a text-only model, the response would be statue. So you can really see that there is some gain from using the video. And we have seen here that we can use this cross-modal learning to exploit the large amount of data online available. So you have automatic data, a small annotated data set, and we can leverage the two together. We can use the correlation between these multiple modalities, here video and language. And open issues are how to further improve the zero-shot performance. We have seen that it's not yet at the same level as for supervised performance. And one example would be to use fine-grained matching and object detection to remove incorrect examples. That's future work. And in the second part, I'll present a new task, which is a transformer-based model for vision language navigation. So what is the goal here? We have an indoor and synthetic indoor environment taken from real pictures and then assembled. So these are existing environments. We have an instruction here, go to the bathroom in the bedroom with orange stripes, make sure that the faucet is not leaking. And then we have an autonomous agent that wants to accomplish this task. And here what's new is we have designed a fully transformer-based model. This model takes as input the text, which is the instruction, then encodes the history, so what the agent has seen previously with the hierarchical vision transformer to memorize the locations and the actions the agent has seen before, and then takes as another input the current observation and feeds all this information in a cross-modal transformer encoder and can then use this encoder to predict the action. And here again, what is important is the losses. So we resort to a number of standard losses for vision language training. So mask language modeling, last region loading, and instruction trajectory modeling. And then we can add new proxy tasks for vision language navigation, such as single step action recognition and spatial relationship prediction. And show that all of these losses improve the performance. The ones on the top are standard ones, and the other ones allow to refine our downstream model. And then we can show that our approach outperforms the state of the art on several data sets by a margin, and it was the winner of the Very and Soon Challenge in conjunction with ICCV 2021. So here we can see that transformers can also be used to predict actions. We have seen that standard vision language losses improve the performance and can be used as for other models. Again, additional pre-training data is useful. And open issues are how to generalize better to unseen environments, for example, by using more training data and how to collect this additional training data. And then obviously it would be nice to apply these models also to real robots. Thank you.
Thank you so much, Cordelia, for that talk. Next, I'm delighted to introduce Ilya Sutskever, co-founder and chief scientist at OpenAI, and one of the people who's done more than anybody, perhaps, to lead to the development of foundation models.
Thank you for the introduction, Chris. I hope I can be heard. Sounds like I can. All right. Well, thank you for inviting me. And I'd like to tell you a few things. I'd like to tell you a story. It'll be a quick story, not longer than 8 minutes, actually shorter than that. One thing that I really enjoy about all of AI is how simple it is relative to how impactful it is. Unlike something like quantum mechanics or some other complicated physics or complicated chemistry or math, AI is really simple. You just have those artificial neurons, which are inspired by biological neurons. And there is a math formula consisting of 3 equations that tells you how these neural networks should learn. It's called backpropagation. And it's the kind of thing which you can explain to a high schooler that knows math in about half an hour. But the magic is that the result has been so impactful. And so what ended up happening is that there is one recipe, essentially one recipe, that's been powering every single thing that's ever been done that's also cool in AI. The recipe is you take a big neural network, a big digital brain running on a big computer cluster that's running this learning formula, which I described to you, that I told you about but did not describe, and you just feed it a lot of data. And then what you'll see next is how we vary this formula, how we change the neural network, how we change the data, and the downright magic that ensures. You know, when I started OpenAI with our co-founders more than 6 years ago, I was motivated by a belief that neural networks will continue to surprise us and to make the kind of incredible progress that they've made. And it's quite likely that the progress that neural networks are making, the progress that they have been making, will keep going on for quite a while. I don't think anyone here believes that neural networks will slow down. And so their impact will be very vast. They will touch every aspect of society, every part of human activity. And so with this belief, we thought to create OpenAI to not only fulfill the original sci-fi promise of AI, to realize it, but to also make it benefit humanity with all that entails. But now I want to go and dive into some of the technical details and tell you about some of the neural networks that we've built. Because time is so short, I will go quite quickly through them. So GPT-3 is just a really big neural network whose training objective is to guess the next word. Well, you could say, what's so special about guessing the next word? The thing about guessing the next word is that it's something you can do in math. You can just measure how good your neural network is at guessing the next word. But if you do a good enough job at that, if you guess the next word well enough, you must understand something. And the better you guess the next word, the better you understand. Imagine a mystery novel where the detective is about to unravel the identity of the criminal at the end of the book. If you paid attention, you might narrow down the appropriate next word down to 2 guesses, maybe even to 1 guess if you paid really close attention. So now you have a link between guessing the next word and understanding. So GPT-3, I think many people are familiar with it. At the time, it was quite surprising and unprecedented that you could just communicate with the neural network in this way, ask it questions, ask it to do stuff, do few-shot learning. It was a big surprise. Now it's been almost a year and a half ago, more. Old news. We're not surprised anymore. Tough crowd to please. One cool thing I want to mention are the use cases of GPT-3. One of the cool things about these models is that they're no longer science projects. very useful. So GPT-3 has been exposed through the OpenAI API, and it's been used in production by hundreds of companies. I'll mention my single favorite use case called the Trevor Project, where they use GPT-3 to pretend to be disturbed teenagers to train therapists to talk with real disturbed teenagers. So I think that's my single favorite application of GPT-3. I think it's legitimately quite cool, if I may say so myself. I'll briefly mention GitHub Copilot. It is a collaboration we've done with Microsoft, where we trained a really good neural network to guess the next word in code. Unsurprisingly, a neural network can do that task quite well also. GitHub Copilot is really popular. Programmers love it. And the users of GitHub Copilot commit 30% of the code that they commit is written by Copilot. So that's a pretty good statistic. And of course, as with all these neural networks, this is not the end point. This is more of an appetizer. Things will get a lot better. You may also have heard that we have made some progress on image generation with DALL-E. You know what it can do. You give it text, it produces an image. Why do it? We've made a lot of progress in text-only models, but the world is not just text. And I don't think anyone here believes that the powerful AIs of the future will be text-only. I'll just show you some cool images that I like. There's many more on the internet, but on the text, you have the caption that produced the particular image. I like this one. I mean, really, those are pretty good images. This one is, I think, caught the attention of many. I think Percy had this one in his slide as well. I like this corgi in the shape of a fish. It's pretty good compositionality, I have to say. You have to understand fish and corgi and the way it would look like if they were to be combined. Fur monster in a purple room. I think it's a very appropriate fur monster. That's quite a beautiful photo of this family of mice with the zoom in, the blurry background. Very artistic. Just a beautiful painting. I think that's quite meta. So I only have 1 minute, but I want to tell you about safety and deployment. You know, as I mentioned, our goal at OpenAI to not only build general AI, not only realize the promise of sci-fi, of the AI sci-fi of old, but also make it beneficial. And what that means is that we will be what it means is that we are building increasingly more powerful AI systems. We make them safe and we figure out how to deploy them. And I'll describe to you the high-level process that we use for deploying these systems in the remaining 30 seconds. And we've done quite a bit of work on this process with DALL-E. And in short, it consists of 3 steps, the high level. We do a lot of planning ahead of time, where we try to think about the many ways in which it could go wrong, the kind of biases that it may have, the kind of misuse potential that we really don't like. We make decisions. How do you trade off the exciting, cool applications with the negative applications? What kind of restrictions do you want to put on it? We do training, where we modify the training data and do additional training after the fact to modify the capability of the system. So for example, with DALL-E, we modified it so that it is unable to generate recognizable faces. It took us additional work to remove this capability. And then, of course, when we deploy our model, we put it on our servers behind an API. And we gradually increase the surface area of its application. And we carefully fine-tune the usage restrictions as we learn the ways in which people use those models and misuse them. This is all I have to say. Thank you so much for your attention.
Thank you, Ilya. Our last speaker in this session before the discussion is Professor Rob Reich from Stanford University.
All right, I stand between you and lunch, and you just heard from a whole series of people with technical expertise. I'm a philosopher by training. I direct the Center for Ethics and Society here, and I'm helping to bridge ethics on campus across to the engineering school as one of the associate directors of HAI. We live, to say something very simple, in an age of AI, agreeing entirely here with Ilya that AI is transforming every aspect of life, personal life, professional life, political life. And these enormous foundation models are the latest and potentially most powerful of the transformations that AI will bring about. And so I want to frame my remarks today, not technical remarks, but philosophical remarks, by sharing a passage that speaks to me and I think is relevant to our conversation today. The passage is the following. What the inventive genius of mankind has bestowed upon us in the last 100 years could have made human life carefree and happy if the development of the organizing power of man had been able to keep step with his technical advances. As it is, the hardly bought achievements of the machine age in the hands of our generation are as dangerous as a razor in the hands of a 3-year-old child. Anybody know who wrote that? It was Albert Einstein in 1932, 90 years ago. What can we do? What must we do to advance the organizing power of mankind alongside our extraordinary technical advances? That's the question I have for us today. That's where I think philosophers, social scientists, humanists have something to contribute to the technical and scientific advances of our extraordinary age. Now, one kind of response you might hear from a philosopher is to insert into the conversation ideals like the following. Let's think about justice. Let's think about fair AI and machine learning models. Let's think about equity, about transparency, accountability, and power. Familiar terms, familiar concepts, familiar ideals from our ethical and political lives. And those are important contributions. I have to say, I don't think in my experience working with alongside technologists that they hardly find them interesting or original, as if technologists were uninterested in justice or fairness or equity or transparency or accountability. They are. And there's enormous and productive amount of work taking place at the intersection of social science, the humanities, and technologists in order to make advances in those particular areas. You heard some of it just earlier in some of the presentations. So I want to take a different tack. I don't want to talk about fair machine learning at the moment. I want to frame for you a different way of thinking about these questions. And that's to identify what I'll describe as 3 different levels, 3 different kinds of points of intervention to think about the ethical and political dimensions of our machine age, of this AI age, of the foundation model age that's just dawning. The first level is what you could describe as personal ethics. Do you have a relevant moral compass that guides what you do as a human being? That's a familiar thing for people on college campuses. It's a familiar thing to talk about in the wider world. We should all have some moral compass that orients how it is we act. And I want to share with you what I find this the least interesting way to think about ethics. Because number one, human beings are not perfect. They routinely fail their own moral compass. Does anyone think that if Elizabeth Holmes had only gotten the ethical reasoning course at Stanford before she dropped out, that it wouldn't have gone the direction it did? Or that other people across any domain of life, Lance Armstrong, Richard Nixon, had only taken enough ethics courses to have gotten their moral compass in order, that all would have been well? No. Moral compass is fine, personal ethics is fine, but we need to organize our lives to assume human frailty and human moral failure, because that's the human condition. So the second level of ethics, the second point of intervention, is what I'll call professional ethics. How is it that people in a profession organize themselves around a common set of norms or an ethic of responsibility to steward their own work, to regulate, as it were, in a soft way, not through law and policy, how it is that the professional domain advances? I want to focus my remarks largely on that area with the last minute or two I have left, but I'll just identify the third area of intervention for ethics, which is social or political ethics. How do we think about formal policy, law, and regulation? Now, the premise of the work that I've done here on campus with HAI and with colleagues in the computer science department and in public policy is that On the advance of science and technology, there will always be an outpacing of the capacity of formal law and policy to be on the frontier in a wise way. So in this race between what you could call disruption and democracy, the technologists and the scientists are always pushing ahead more quickly than how regulators can knowledgeably act. So I draw from that general observation a reflection that many people in the room might share, that there's a kind of suspicion of DC policymakers getting in the game now to think about what OpenAI is doing and putting in place a set of regulatory guardrails. Instead, we need to think about professional ethics, professional norms that organize the work that we do as AI scientists, because we shouldn't count on the ability of regulators to keep up with the frontier. And so, thinking then about professional ethics and professional norms, I'll just offer up an invitation for you to imagine a comparison between the professional norms that guide the field of biomedical research as compared to AI science. In biomedical research, we have things as old as the Hippocratic Oath. We have professional licensure requirements. We have the institutional review board that guides any type of work with human subjects that happens in universities or in pharmaceutical companies. We have a federal administration, the Food and Drug Administration, that's required to give permission to anything that's released on the market. We have an entire scholarly field called biomedical ethics that has grown up over the past 60 to 70 years. We have hospitals and companies that have ethics committees as a routine part of their organizational practice. Now, AI is, by contrast, a developmentally immature domain of scientific inquiry. AI has only been around, computer science has only been around as a field, formally speaking, since the 1950s and 60s. And given recent developments in AI that have taken place just in the past 15 years, this neural net age, it's much younger still. So to put it in a provocative way, what I would invite you to think about is the idea that AI scientists lack a dense institutional footprint of professional norms and ethics. They are, to put it even more provocatively, like late-stage teenagers who have just come into a recognition of their powers in the world, but whose frontal lobes are not yet sufficiently developed to give them social responsibility. They need a rapid acceleration. We need a rapid acceleration of the professional norms and ethics to steward our collective work as AI scientists. Think, for example, of Jennifer Doudna, the other twin revolution that's shaping the 21st century in gene editing and CRISPR. She wakes up, Walter Isaacson tells us, from a dream, a nightmare. What if Hitler had access to this technology? And she organizes her professional peers within the professional bodies of biomedical research to impose a voluntary moratorium on the use of CRISPR on humans or human embryos. No one will be allowed to publish if they cross that moratorium. They won't be invited to professional conferences. There's a strong professional norm in that domain. AI scientists, to the best of my knowledge, have very few institutional touch points that parallel biomedical research, and I pin that on the idea that it's a younger field. So as we hear from Ilya and others who are at the forefront of pushing the technical frontier forward, my question for us, who is organizing the organizational and institutional and professional ethics to accelerate at a pace that matches our technical advances? I'll conclude with just 4 simple questions specifically about foundation models. Number 1, we know that there are huge risks. We've heard about misinformation, disinformation on steroids, about job displacement. Sam Altman tweeted out last week after some of these announcements that we thought for a long time that AI was coming for the jobs of low-skilled workers, but it looks like actually it might come for high-skilled workers first. Coders, illustrators, writers are the ones that will be displaced, not truck drivers, or at least in that order. And then there's a huge concentration of power. This is the paper that Percy referred to, the opportunities and risks of foundation models. So, question 1, what are leading AI scientists doing to accelerate the development of professional norms? What counts as responsible development? To put a question on the table for OpenAI, I hope Ilya can speak to, I know that he can, he has in the past, about the shift from GPT-2, in which there was a restricted release, a kind of policy override of what otherwise might have happened within AI science, to a different orientation now with GPT-3 and beyond. Number two, as someone who writes about democratic theory, you might be surprised to think that I am suspicious of the idea of democratizing AI. We don't want to democratize access to some of the most powerful technologies to put them in the hands of anyone who might use them for an adversarial purpose. It's a lucky thing that access to plutonium and uranium is not democratized, and it's easy to organize limiting access to it. But with AI models that are in the world open for anyone, we're inviting adversarial use. How can we move away from democratizing AI in that respect, but opening up access to independent researchers? Third and last question, we need to think about the political economy that exists. No university is capable of putting together the compute and the data sets to make these models on the frontier. It's for-profit or capped for-profit companies that can. We need to think about issues of brain drain, about commercial incentives that drive the scientific frontier rather than scientific inquiry and non-commercial incentives. All right, questions, provocations, not answers. Thanks for listening.
Thank you, Rob, and thank you to everyone who spoke on this panel, including Cordelia Schmid, who's being represented by that large video monitor down the left-hand end to be as part of our panel. Okay, so for the next half hour, we're going to have discussion and questions. So it looks like I don't really need to say this next bit of coming to the microphone. There are 3 microphones if you'd like to ask a question. It seems like there are lots of questions, including the very big picture questions that Rob asked at the end of his talk. I'll just ask one while we're getting started that is much smaller than some of the questions he asked. But I mean, so for foundation models, there are clearly safe uses. So Ilya gave one nice example of a safe use with the Trevor project of training suicide hotline people. And that's very safe because that it's just used for training. I mean, using codecs for coding sounds fairly safe too, though you could imagine that there are things that go wrong there. But it seems like there are also a lot of uses that aren't safe. Do any of you have any thoughts as to how one can define the boundary between safe and unsafe uses of foundation models?
Maybe we can start. I would actually say, I mean, codecs has potential problems. I mean, imagine a code that you're generating that, I mean, people already don't necessarily understand the code that they're generating, and if AI is generating the code and it seems to work, you could have kind of insidious security vulnerabilities that potentially slip in. I mean, I think this is generally a good question about dual-use technology. There are some places where if you're trying to do drug discovery using a large foundation model, that's perfectly fine. But if obviously on the other end, if you're spamming or engaging in fraud or disinformation, that should be outlawed. I mean, this is where I think it's at the less at the technical level, because the technology is by design just capable of things, but at the kind of process of terms of use or kind of having a more of a system in place for tracking kind of what these models are released for and what can people use them for, and having mechanisms for if something is misused, having ways of reporting. And I think we lack that infrastructure right now because the emphasis is more on kind of training these models, but the models need to kind of exist in a larger ecosystem.
Yeah. Anyone else have a thought? Yes, Sarah.
Well, I think earlier in the panel, somebody talked about PII as a result of just querying the systems, right? Presumably, do we consider that unsafe use? And if we do, then the boundary for safety is very different.
I'll just add that there's call it a small scholarly field of research done under the heading of AI safety that applies in particular to questions about the aspiration to reach AGI. So that's one place to look for an answer to these questions. But from my point of view, thinking about this as a political philosopher, not just strictly as a moral matter, any large picture questions about what we define as safe or unsafe uses seems to me necessarily to extend beyond the purview of any technical expert or even company. Having an AI safety team at a company is all well and good, but ultimately questions about safety are social questions that deserve input from multiple stakeholders.
Okay. Well, maybe I'd better start turning to questions from the audience. Maybe I'll start with the very back mic person. And it'd be great if you could just sort of introduce yourself very quickly before your question.
Yes, I am Ethan Hamilton. I got a PhD in electrical engineering from Stanford, and I work as a software engineer in a local startup. So I have two questions, one very short for anyone, probably Ilya. How much does it cost? Everything, training, salaries of the researchers, you name it, to produce one of these foundational models, to know how high the barrier is. So that would be the first question. The second is for Rob. I want to challenge, so I agree with that there is a problem, no question, but I want to challenge the FDA as the perfect model. ProPublica has made a great reporting about each of the large big pharma companies has been fined for malicious marketing of drugs. It's a legalized drug cartel. Do we want to create another one of those?
Okay. So Ilya and then Marc.
Thank you.
Yeah. So I can't comment on the precise cost of these models, but it is indeed the case that they are not cheap to make. And it's not just the compute. You also need to have a really strong team working together for quite a while. So yeah, I mean, my expectation is that for if, let's say, universities want to participate in the creation of these models, they need to do what Stanford has done, which is to basically band together and organize a lot of resources. And in particular, I think that one place where universities need to build some muscle is on the engineering side. Because you can get money, you can get compute. But then the natural way in which universities do research is different from the kind of organized effort that's needed to really push such a system. So I think that this would be another organizational hurdle that universities would need to overcome to participate.
But it's in the range of, say, tens of millions of dollars, hundreds of millions of dollars. It makes a difference, the range.
I understand, but unfortunately I can't comment right now.
Yeah, I think there are some papers you can read on that, but let's turn to Rob.
I don't mean to point to the FDA or the idea that we should create an independent federal agency, the Digital Technology Agency or something. I meant that as an analog. Here's what biomedical research has built out over the course of decades, and here's what is absent from AI science. I don't think we port the professional norms and institutional design from one domain over to another domain. So I mean it as a way to think about the density of the institutional design. And of course, we need to come up with purpose-built answers for the age of AI.
Okay.
I have a question for Ilya, but for anyone in the panel. Given all the advancements in multimodal, multitask foundation models, how do you define AGI? What are the milestones to get there? And is embodiment key for it? Or what are the other requirements people aren't talking about?
How to define AGI? So it is indeed the case that AGI is a little bit of an ambiguous term. It's not used very precisely by people who use it. It should be understood as more of an aspirational goal, kind of like a North Star. And the way you can tell that we have reached the age of AGI is when you have lots of computer systems. Like one way to tell, here's one way to tell, is when most of the economic activity is done by some kind of an AI. This is an objective criterion. Because if someone comes to you in the lab and says, oh, check out what I got, how can you really know whether you're being shown something real or not? But if you are living in a world where the economy is growing really fast because AI is doing the great majority of all economically valuable work, that's how you know that AGI has been reached. I mean, I think that the current models are really exciting. They're making a lot of progress. And like the way to really measure their impact is like how much are they being used to in the real world to actually solve problems. Like I would say that right now, these models are just breaking out from the lab. Until very recently, AI would make a lot of exciting progress on benchmarks in the labs. It would be really cool science projects, just starting to get out, starting to impact the real world. So there's still lots of work that needs to be done. The models need to get so much better, so much more reliable, need to explain ourselves, really collaborate with us in order to solve problems. All these things need to happen. We are seeing very small steps in that direction. Things will be a lot more exciting in terms of how much these systems can do.
Okay, let's take a question from Fei-Fei, and then you'll be after that, Pat.
Yeah, okay, I'll start with the intriguing technical question, possibly mostly for Ilya, but interested from the technologists too, is that when we look at that corgi fish picture from DALL-E, frankly, for average human, it's very hard for an average human to draw a corgi fish. In the meantime, for average human, it's very easy if I ask you to draw a toy cube tower that would fall under gravity. Like that concept of a simple tower, toy tower fall. So there's a discrepancy. I think that's going to be hard for DALL-E. So there's a discrepancy between what's easy for human to generate and what's hard for machines. Do you want to comment on what in the making of these transformer models that create this discrepancy between, DALL-E and humans?
Yeah, I can comment on that. So I'd say, so that question, there are actually two different sub-questions. In the case of DALL-E in particular, it was designed, there were certain engineering and design choices that were made, which are not inherent. They were made for convenience in order to make the system have certain better properties. So because of that, it is not as good at some of these tasks which you mentioned, but those limitations can be lifted. I do want to point to a deeper, more fundamental difference between these neural networks and human beings. These neural networks, they have more breadth and less depth. Like if you consider a language model may have read far more books than a human being ever would. But a human being understands the information that they've consumed more deeply. So I think that this is the more fundamental discrepancy between human beings and AI. So it is indeed the case that there are many more scientific breakthroughs that can be made to improve those systems. Despite this discrepancy, there are still clear avenues for improving those systems, and so they will still get a lot better. And perhaps over time, those discrepancies will diminish as well.
Maybe I can make a quick comment in response to Fei-Fei and the last question, which is how one should kind of think about progress. Because I think AI traditionally has been viewed as kind of autonomous systems where you measure them in isolation. But we know for a fact, especially when they're deployed in the real world, we hope that they would be under some control or aligned with values of humans. So I think human beings have to be part of the picture. And then you go back to kind of thinking about economic impact. It's not clear how that aligns exactly with this kind of age-old dream of building human-level intelligence. In some ways, that may be not even relevant, because what we really want is tools that help us build a better society. And if they can't do certain things that humans can, that's perfectly fine, as long as they can do a certain well-defined set of things well, robustly, in an unbiased way. I think that could have a tremendous amount of impact. And I think that maybe framing is maybe a way we should be thinking about assessing the value of these technologies rather than measuring it against a kind of a human yardstick.
Okay, let me get a question from Pat.
Sure, thanks.
Cordelia.
And this is mostly for Chris and Percy, who can probably guess what I'm going to say, because I say this after every talk I hear at Stanford. So the best science and the best engineering builds on previous work, and the failures and the successes of that previous work. Now, AI has a long history of successes and failures, but we've had deployed AI systems in industry since the 1970s. We had deployed systems that were built using machine learning by the late 1980s. Long before deep neural networks became a thing. And in natural language processing, there were a bunch of systems that were used for various applications using classic natural language technology, and you guys were trained with some of this. I know you still cover it in some of your courses, but when I hear you talking about foundation models, I grant that there's been plenty of progress and the results are impressive, but it would seem to me there must be some way to bring together that progress and some of the classic ideas to get the best of both worlds. In particular, in a meeting on human-centered AI, some of those older approaches are far more connected to what we know about how humans process language. So can you say something about how we might do that, or if you think is that a bad idea?
Okay, I think Percy, you'd better take that.
Yeah, I can definitely take it. I think there are certain things that are age-old and will never disappear. That we should think about, kind of knowledge, representation, and kind of reasoning. But there are also a lot of things which in the 70s are probably not relevant today, given kind of what we know about how capabilities. I think that one way I think of these technologies is they're very good system one. They can instinctively kind of generate things on demand. And but for very long-range, sophisticated reasoning, they're getting better, especially with some of the latest kind of multi-step reasoning things. But they're not quite there, and they certainly don't have the crispness that we have. So that part is still missing. I mean, one outstanding question is whether we can get there. I think that is open with the kind of existing methods. That, I think, is an open question, and I like to be kind of open-minded about it because, in the last few years, I've been surprised. I think everyone has been surprised how these technologies work, and I think, but I think holding on to some of the kind of the principles of how you can generalize, I think is very worthwhile.
For example, you could imagine using...
Pat, I think there are a lot of questions, so maybe I think we'll have to move
offline.
on. You can you can talk to Percy later.
And my name's Pat Langley. Thanks.
Let me try and bring Cordelia into the conversation. So picking up on that theme of being more human-centered, so there's been productive work on multimodal models, but most of the visual work has used just images, and that certainly stands in distinction to human learning, where not only do we have the equivalent of video, we're seeing this moving world around us, but human developmental studies have shown the absolute importance of interaction for little kids to learn, right? So just watching videos even isn't very effective. So does that mean for multimodal foundation models we should be doing something quite differently? I mean, to put it most provocatively, one could argue that something like DALL-E is really a sort of a dead end because it's not really heading us in the right direction for human-level artificial intelligence.
Yeah, I think we should...
Can we see if Cordelia, do you have some remarks?
Yes, I think I would agree that basically the next step is really using video because you have all the motion information. I mean, basically Fei-Fei's example for tubes falling, you need motion information to learn from them. You have all the corresponding information with audio and speech, so you have a much richer corpus of information, right? And I think you can also see obviously the video as an extension from the images, right? It's not because you can generate an image from text. The next step would be you could generate a video from a sentence, right? So I think it's not either or, but I would say video allows you to do much more And then I guess Video has the multimodal information. And one thing of these foundation models or these transformer models that they can really capture this multimodal information very well, right? It's much easier to design multimodal representations with these models because they can learn automatically what corresponds between the different modalities. And then obviously, if you want to go towards more general intelligence, you need to also interact with the world. But that's something I think we don't, I mean, we just start to see how these models can actually integrate interaction with the environment. And so I think that would be the next step.
Okay. Do you have a comment, Ilya?
Yeah, just a brief comment is that one way we can think about the progression of these models is that of gradual progress. We've made a lot of progress in text-only models, and we were surprised by what they can learn. We have added another modality, perhaps not perfectly. Perhaps this is not the final way in which we will add the modality. Some exploration will need to be done. But eventually, I think it is a reasonably safe bet that we will figure it out as well to find a very useful packaging of the modality so that the system will know more, understand the human world better, and be able to interact with us better because of them. So it's a technical problem that will likely be solved.
Okay, great. Right up the back, yes.
My name is Evelyn. I was a Stanford student, and I took my first AI class with Professor Liang. So I really appreciate it, Professor Liang. And you mentioned the process of adapting a general model to a specific domain. So I guess my question is actually to Ilya. I have built an application using GPT-3. And by the way, OpenAI has a very good safety review process. I went through the process, got the approval, and rolled out a global launch. What I observe is that the option to customize the general model to a specific domain is very limited. Although there are options, but it's very limited. So my question is, what is OpenAI's plan to allow more customization and configurability of the GPT-3 or DALL-Es?
Yeah. I mean, you should expect that that the ability to customize these models will increase in the future, customize them through fine-tuning. I do want to make, however, so I should say, it will become easier and the tools to do so will become more powerful. But I also want to make one other comment, and that's about the shape, the likely shape of customizability of these models in the future. One point of view, which I happen to believe in right now, is that if you take a model, any neural network, and you have some kind of benchmark, and you fine-tune the neural network on this benchmark, you'll get really good performance on the test set. But that doesn't actually mean that your system is that good. And that's something we've seen a lot also. I think it was most apparent in the kind of intermediate years, maybe like the mid-2010s on ImageNet, on the ImageNet dataset, where people started to report human-level performance on ImageNet. Yet the systems were obviously not human-level not at the human level. So what does that mean? Like, I think what that means is that there is hidden overfitting going on when you fine-tune. And so I think that several things will need to happen. Like, the fine-tuning technology itself will need to improve so that you'll be able to preserve a lot of the generalization of these powerful base models. And we'll actually find that zero-shot evals give you the best and most reliable, like, representative performance. What you can get zero-shot or few-shot, you know that's on your test set, you know that's the performance you're going to get in the wild. So it's a much more honest measure of performance measure for yourself as you evaluate your system.
Okay, sorry.
Yeah, perhaps this question is best suited for you, Professor Liang. I was just curious, what is the academically precise definition of this so-called foundation models term? Like, models are getting bigger, they use billions of parameters. They're able to generalize beyond expected tasks. Like all of these are nice properties of some of the things we're observing. But I'm wondering if there's a precise way to say, okay, this is a foundation model and this isn't. I mean, is it a vague sort of comment on an industrial inflection point, or is it actually something that we can say that this is a foundation model?
Yeah. That's a good question, and we spent a lot of time thinking about this. We actually have a blog post on our website that explains the details, but just in brief, it's a spectrum. Is BERT, let's say, is Elmo a foundation model? Maybe. BERT is probably a foundation model. GPT-3 is definitely a foundation model. The definition I gave in the talk is a model that is trained on broad data and can be applied to a wide range of downstream tasks. Now, those are fuzzy terms, but I think the breadth of the data is important because that's, and also when you talk about broad data, that implies certain other features such as self-supervision and training at scale, because without those, you can't really train on broad data. And so I think many, you could think about breadth and the kind of as the kind of key defining factor, and many of these incident, whether you use a transformer or use backprop, those things kind of follow out given where we are in terms of the technology. In 10 years, maybe we'll have, we won't be using transformers, we'll be using something else, and we'll be training in a slightly different way, maybe with reinforcement learning, but that doesn't change the kind of the essence of a foundation model.
So any large model trained on a wide breadth of data is a foundation model?
So a model that's trained on a broad set of data and can also be applied generally. Yeah.
Okay, Fei-Fei, let's take one more question from you.
Okay, this question is absolutely inspired by Rob, so by Rob's talk, as well as for the past 3 years, he's worked with me on this and inspired me, but I'm asking this to technologists. Rob talked about the need for professional norms and ethics, and Rob has also inspired all of us at Stanford to think about baking ethics into the design of algorithm. So I want to ask Cordelia, Ilya, and Percy, when you are building your foundation model, big or small, what exactly are you doing, or your organization, are they doing baking ethics into the foundation models?
Yeah, I could comment on OpenAI's process around the way we go about releasing these models in a way that allows us to capture as much of their beneficial uses as possible, while contain their harmful uses and contain their harmful biases that we don't want exposed as much as possible. I mentioned it in my last slide of my presentation, and I want to elaborate on that. So, we think about it a lot, and we see us finding good practical answers to these questions as a core part of our mission at OpenAI to build general AI and make it benefit humanity. We want to figure out how to actually deploy these systems with each new level of capability. I'll mention an anecdote. When we trained GPT-3, we kind of already foresaw many of those issues. And so we had we also had the luxury that no one else had such a model. So we took a very long time. It was almost a whole year where we manually reviewed every single application request to use GPT-3 somewhere. And we built a very large amount of institutional expertise around the kind of use cases that are okay, the kind of use cases that are more objectionable. There have been some ambiguous calls as well. And the process that we've converged on today, that we will continue to refine, is one of, we look at the capability that's about to emerge, and we try to anticipate and categorize the different uses that we can predict just by thinking. We make a list, and we say, okay, this looks exciting and we want to support it. This looks like we really don't want to support it. We then make a decision on the basis of those predictions around what will be the next step. So for example, we might modify the training set using filtering, or we might do additional training on top of a finished model. So for example, we've had work recently that we've announced where we used reinforcement learning from human feedback to teach a GPT model to follow the intentions and the instructions of its users much more closely, to be more aligned. We've done this work. And then on the third step, the models are on our servers, and we have very precise controls on the kind of queries we want to serve and the kind of specific applications and uses that we want to support or not. So there is a usage policy as well. So that
maybe you should get thoughts from others at this point.
Can I interject?
I let Cordelia give her thoughts on professional norms first, and then Percy.
Yeah, I would say it actually joins the question about what data we use to train these models, right? Because if we don't know what data goes in, we have no guarantee what comes out, right? And this, I think, is a central point that we have to understand much better which data goes in. And for language, I think we know which corpuses the data comes from. This gives us some guarantee that for example, we train it on books, that there's not misinformation per se in there. But if you have any random content, you really need to curate the data. And I think this is like one of the things which are really key, to know which data goes in. So this is the first thing. And the second thing is to make these models more interpretable. To have an idea why this answer was given, where it comes from, to backtrack and then maybe remove the data.
Maybe just one follow-up to Ilya's one. I think it's great that OpenAI is taking these measures to ensure the safety. I think it's not enough in the sense that there's a kind of a certain sense in which these models surface area is so broad. I don't think any individual team, let it be OpenAI or Stanford or anyone, has the ability or even the authority to really determine what decisions to make. And I think there's some tough trade-offs. For example, how you filter. If you filter toxic information, you could marginalize certain groups. And I think there's constant tension here that I think demand kind of a much more public and visible kind of discourse. And also I talking to many kind of large foundation model developers, people have very different opinions and norms about release, what's safe and what's not. And I think we should be acting more coordination as a community to figure out get on the same page with respect to what are the kind of the issues, what trade-offs, and it's fine to disagree because everyone has slightly different values, but also kind of use cases, but there's a certain kind of consensus building that I think we're lacking a need here.
Rob, do you have a quick
thought? I mean, for anyone here, but just this response to Ilya's remarks, underscore that I agree with Percy that if we're talking about a foundation model that has these general adaptations, whatever the size of the team is at OpenAI, and however hot-housed and long the process was in trying to imagine use cases that you wanted to try to intercede or limit, well, if millions or potentially billions of people had access, presumptively, they would come up with use cases that you couldn't imagine. So that makes me wonder, since no team, agreeing again with Percy, possibly could imagine all possible use cases, how about talking openly and publicly, looking for feedback on whatever the framework was that you used internally for identifying beneficial and malicious, or however you describe them, use cases. What was the framework OpenAI used in this year-long process, however long it was, in order to sort out what counted as worthy and unworthy use cases?
So I want to make a comment on on the first part of the question. Another important part of the way in which those models are released is that they're released gradually. So rather than say, hey, we've got a new model, billion users, please start using it, we're going to say, well, let's start with 100 users first and see what they do. Sure. And learn from that. And then you release it to the next 100, the next 500, and you fine-tune the policy and the various controls that you have on the basis of those experiences. So in other words, instead of doing a very big discontinuous release and maybe finding yourself facing a crisis, you have very small releases, and so you're able to productively learn from whatever happens and bake it in. And this graduality is very important. There is another thing that I want to mention that will be increasingly important in the future, is that the AI capability itself will be helping us with making these decisions. At present, AI is not good enough in order to, and it cannot be counted in order to help decide on use cases and explain why a use case is good or not. But in the future, I expect it will change. And that will be a very important tool in the toolbox of deploying such systems and dealing with their large surface area. I would say, and to your question of the specific framework that we used, so this stuff was very new when we were doing it, and so we've taken a pretty restrictive and a conservative approach. We have decided that we want to err on the side of caution. That would be my general description of the framework that we've used. And we figured we'd rather start restrictive and gradually expand it, as opposed to start overly permissive and then contract it. So that might be the one-sentence summary of the framework.
Okay, I think I'd better cut things off there. This is a great discussion. I'm sure we could spend another hour just talking about the answer to Fei-Fei's question alone. And I realized there were other people that were hoping to ask questions. I'm sorry, but we're already eating into lunch hour, which seems a bad thing. So hopefully you can answer your questions either by cornering the speakers during lunchtime or with other fellow lunch eaters, or else you could send them along to HAI. But anyway, thanks to our panelists one more time for the engaging discussion.